Hello, I'm Daria Phoebe Brashear, and this is Hands-Off Testing for Networked File Systems. Today I'm going to talk to you about what distributed file systems are and what our product AuriStor is and how it works. I'm going to talk to you about continuous integration systems, and then I'm going to give you an in-depth view of Buildbot, TAP, and creating and running tests. I'm going to talk about doing testing from the wrong side of the kernel abstraction, and then I'm going to talk about lessons and future work. So the idea of a distributed network file system is no matter where you go, there your files are. The godfather of network file systems, as it were, was Carnegie Mellon's Andrew file system from circa 1983. At the time, Carnegie Mellon had gone heavily into the idea of a distributed campus in terms of network resources, so that hopefully every student could have access to a computer and could do their coursework online. At the time, this required patching kernels, and people were using BSD Unix. The virtual file system concept wasn't even introduced yet. So if you wanted to make changes to file systems, you basically needed to make changes to the operating system itself because there was no concept of using anything other than the single local file system it supported. Sun's NFS came around about a year later. It introduced the concept of SunRPC, which is remote procedure calls. And this was later adopted back into what AFS did in place of its own RPC mechanism. But at the same time this happened, there also was introduced the concept of a virtual file system. And that would let you plug other file systems other than the basic local file system into your operating system kernel. AppleShare came along for Macintoshes, which weren't true Unix machines like they are now at the time. Windows got SMB, server message block, and then later SIPs. And of course, Solaris introduced the concept of ZFS, and all of these are examples of distributed file systems. So a moment to tell you about what I do and who we are. AuriStor was founded in 2007. We came from the lineage of OpenAFS, Transarc AFS, and Transarc, of course, being bought by IBM, so IBM AFS. Unlike OpenAFS, we are a fully commercially developed and supported product. Cross-platform, we support Windows, macOS, Linux, Solaris, and web, and we have in the past also, and will again at some point, have mobile clients. Highly scalable, highly available, secure transport mechanism, granular self-administered access controls, both in terms of who can create groups for access and how they can be applied. And there's a unified namespace, which is to say that whatever path you access will be the same on any other computer as it is on the one where you created it. So in short, our goal is to make it so that your files are available to you no matter where you are, your files everywhere. So I should tell you a little bit about the architecture of AuriStor and by extension about AFS. The idea is that the AFS namespace is split up into volumes, and a volume is a lot like a mini file system. It has a hierarchy that starts at the top and goes down and contains directories and files. It introduces the idea of a special node called a mount point, and this lets you create an attachment point for another volume inside a volume by name, so it will, unlike systems that need special auto mounter tables, you will always find the same other content when you traverse that mount point. Each volume can live on one or more servers where there is a single read-write copy and as many read-only replicas as you like. The read-only replica on the read-write site is free and uses a copy on write mechanism to only use additional space for the differences between the read-write and the read-only copy. And other read-only copies, of course, are a full copy of the data. This uses a publish model. So you pick an arbitrary point in time and you publish a copy of the content to all of the read-only copies, including the same site copy. And then all of this is accessed by clients, which are usually configured to cache copies of the data locally. They can be configured not to, but by default, you will have a cached local copy to avoid extra network traversal as you need to get the data again. So all of this needs to plug into your operating system's virtual file system layer. And the way this works basically for a network file system is that there is an abstraction that you fill in that gives you things like read, write, open, close, open and read a directory. Well, for a network file system, you simply call network procedures to do these operations. For AuriStor, we also have the ability to cache things locally. So we introduce a special path that allows network accesses to instead be short-circuited and go directly to the local file system interface. Well, the thing about this is it means that we've introduced a dependency between the network file system, as it were, and the local file system, so that any copy that you are fulfilling that you already have in your local cache will be fetched locally. And any data that you fetched fresh will be stored directly into the local file system as well, so that it's there for later for as long as it's valid. Now, you can bypass this mechanism by using a memory cache where all of the information that you're caching is stored in memory, but of course that only lasts for the uptime of the system, where a disk cache can basically be used indefinitely as long as you keep revalidating the data that you have. Okay, so now that you have an idea of how our system works, let's talk about continuous integration systems. The idea here is that attaches to your version control system, whatever you're using. The best ones are agnostic and can attach to whatever version control system you want. It pulls in changes as they are pushed to your version control system and then pushes back results after it does testing on them. Basic cases are every time a change comes in, compile it for all of the systems that you support on all of the platforms. And that's useful. It means that you're not checking things into your tree that are going to break. Well, for the definition of break, that doesn't necessarily include whether it works or not. Then there are more complicated cases when you want to start testing things like that. Regression tests. Did you break a thing that you already fixed once? Unit tests for all of the various subsystems you have. And depending on what your needs are, you can go with different systems to do this. Some of them are self-hosted, some of them are cloud-hosted, some of them allow you to do either self-hosted or cloud-hosted or some hybrid thereof. We chose Buildbot. Buildbot is written in Python. It is repository agnostic, which is to say it can use a version control system that you want. In our case, we use Git. Git allows us to have grouped changes where all of the changes related to a single issue will be all part of the same commit. And, you know, at this point, most version control systems that are at all modern have this. If you're still using CVS, I'm very sorry. And the idea here is that there is a build coordinator which pulls your repository for changes, pulls them in, pushes them out to build workers, which build them. It collects the results, and then based on what it collects, it sends the status off to whatever mechanism you want. It can do email or web or IRC, or, you know, there are countless integrations, and if you don't like the integrations that exist, of course, you could write additional ones. So we get from Buildbot the idea of a waterfall, and the waterfall is the results of recent builds. And you get the 10,000 foot view, where basically, you know, is it green or not? And, you know, green is good, red is bad, and then there are other colors for odd conditions. And you can see on this waterfall that most things are green, but we had a couple of failures in the builders that just do packaging, and we had a failure in the builder that runs one of our check suites. So when I said before that we use Git, that's not quite the whole story. We actually use Garrett, and Garrett is a project that came from Google that they use internally to manage their source trees. And it comes with a built-in review interface that lets you manage your tree and review your changes and do collaboration thereon. And so as every change comes in, it gets a new effectively incident created in Garrett where all of the review comments, all of the previous versions of the change, what ultimately gets merged, all of the things related to it are all grouped together. But another thing that happens with Garrett is that because it is a specialized Git server, it has something called an event stream. And Buildbot can take advantage of this event stream. So rather than polling your Git tree for changes periodically and needing to have like a poll interval where, depending on how often you poll, you might go 5 minutes, not notice changes that were already there that you should have been building. Well, instead, Garrett sends an event whenever something comes in and says, you should start building this. And Buildbot, of course, picks up all of the things that have changed and starts farming them out to its build workers. And you can see on the right here, I mean, this is a very busy slide, but you don't really need to look at the fine details. You can see that on the right, I've drilled into a particular build, and you can see that Buildbot claims that it verified and includes links to the results that are buried in the Buildbot per builder logs. So running tests. The best way to do things involves using a test harness. You could write a script yourself and do all of the driving for this with a script, but it's going to be tedious. It's going to be non-standard. If the person who writes it leaves, then perhaps the next person isn't going to like the way they did it. It's not going to work the same way. The expertise is going to be specialized in a way that isn't useful. So if you can use something that lets you basically tie all your tests together in a standardized way, your life is going to be easier. We settled on the test anything protocol. The test anything protocol is a simple text-based protocol that was introduced for Perl in 1987. It's a very simple model. There are other integrations that exist. We make heavy use of CTAP harness. CTAP harness was written by Russ Alberry when he was working on INN, the NetNews server, at this point, over 20 years ago. And because our code base is heavily in C, we actually needed to basically tie our API into something that would let us feed the results from testing it into the test harness. So testing with TAP is very simple. There's test producers speak the TAP protocol, and then there's a test consumer, which consumes all of the results from this and does summarization in whatever way you want. Very simple, can we do something, yes or no? You return okay or not. And the simple results from this give you the ability to summarize all of the information very readily. You can say this test was meant to run, or this unit test was meant to run 3 individual tests. 1 and 2 passed, 3 failed. You can make it so that a single failure doesn't bother testing a large group of subtests, so that, for instance, if you're testing an authentication system and the authentication backend is down, you don't bother running tests and generating bogus failures for something you couldn't actually test. So this is just a sample of one of our tests. This is a very simple one. In this case, it checks the systems that are the build workers to confirm that all of the dependencies are met, that we have a temporary directory we can use for our build to put temporary files and directories in that actually supports things like POSIX extended attributes, which we make heavy use of in our backend system. We make sure that we have an IP address that we can use, which is important because it's a network file system we're testing. And then we have a bunch of Perl modules that we use to generate various parts of our tests that we make sure all of those are installed because they're not part of a standard Perl install. So this is the very first test that we run. And while we don't necessarily turn off parts of the test suite based on the results of this, if any of this fails, it means that the rest of the results are suspect and aren't necessarily treated with the same concern that they would be if they failed otherwise. So the next thing you need to do is actually build out your test suite. And because you're going to be new with this, start small. Start with your basic low-level API tests, things that are going to be simple to test. Start with things that aren't going to have unusual dependencies. And if you're testing something like a network file system, this matters because one of the unusual dependencies you will have is a network. So we have API tests that test everything from very simple low-level operations like manipulating timestamps up to the level of interacting with volumes, which I mentioned earlier, which are sets of files, or setting access control, or things that basically manage all of the underlying bits of a network file system. Once you've gotten your simple tests done, you can start getting into things that are more complicated. As you do it, it probably makes sense to group related functionality. If you're going to be linking libraries in that you need to get the dependencies right, obviously, once you've figured out those dependencies, having all of the tests that take advantage of those together is a good thing to do. And it also means that you can leave systems in a known state from earlier tests where you create something in one step that a subsequent step is going to need without needing to basically tear down and spin up additional test infrastructure that you would otherwise need to do if you were literally going to test every single change individually. So you'll obviously want to grow gradually. You'll do things like adding an RPC client and server test for your network file system. And in this case, what you're going to end up doing is you're going to end up marshaling data when you call into the client, unmarshaling it on the server, doing something with it, and then marshaling up the result, sending it back and unmarshaling it. And that's a very simple way of testing your RPC system. But again, your goal here is to figure out when something breaks, what broke, without having to tear it all down by hand and work out what exactly is going wrong. So you're going to want to test everything. We start with a version which spins up locally the entire system and manipulates it. And remember that spinning up the entire system means the server-side processes. We're not necessarily going to need to interact with it as a client. We just want to make sure all the services come up and can talk to each other and that you can create and delete volume sets. Then your next step is doing client-side testing. Well, it turns out you can do client-side testing without needing to do anything with the kernel. We have more than one client that runs entirely in user space and just makes RPC calls based on the arguments that you give it from a command line that you can use to test much of, but not all of the client code. So, okay, that gets you further, but you still need to keep going because there's still code that you're not covering. You can virtualize the kernel space client code in order to test the actual kernel bits of it. And of course, you're going to need multiple server nodes so that you can test that. And virtualizing is another way of letting you create multiple machines where you don't actually have one and create complicated network configurations where you don't actually have to manage network infrastructure. Then you get to the fun part. Not every platform that you have is easily virtualizable in a way that can be harnessed. Solaris Spark, for instance, provides ways of doing virtual machines and containers, but it's not something that you can necessarily easily spin up and tear down, arbitrarily create, or write a harness around. So we start by virtualizing tests. And among the tools that we have available to us are Docker. For Docker, we create multi-server functionality tests using Docker containers. We use a pre-built OS container, and we also do cross-system compatibility OpenAFS tests by using an OpenAFS container that has pre-built OpenAFS binaries because we're not actually building or testing OpenAFS ourselves. We just want to know, does our system interoperate with OpenAFS in ways that would allow customers who are already using OpenAFS to migrate to our system? And this gets you the ability to very simply run multiple servers and do tests against them where you're not necessarily doing anything complicated with a client. KVM, on the other hand, is hosted by the system that you are running the tests on, and can very easily boot the same kernel that your test system is running, in which case all of your builds that are built that include a kernel module can test that same kernel module in a virtual machine running on the same host. So that gets you most of the rest of the way to where you want to go as far as testing, but still not all the way there. Nested virtualization can be used to test the client code directly on the system with multiple server nodes. And in order to be able to do this, you actually need systems that support it. And while this used to be a hard thing, it turns out modern VMware ESXi just includes a ticky box if you drill down into the processor menu and you enable hypervisor applications in this virtual machine. And you can find this elsewhere, but basically, this is the pop-up from VMware Fusion where you can configure it on. So we're still not directly harnessing the VFS when we do this. We can emulate it. We can do file system and user space to emulate what we would do with the VFS. And file system and user space provides an in-kernel VFS abstraction stub, and then calls out to user space to do the work for each of the routines in the VFS would call. Calls the same vnode operation backend code that the kernel does, but there are some reasons why this isn't still a complete test. It uses different memory pools than you would use if you were working directly in the kernel. It uses different locking structures, and it doesn't actually exercise your own VFS linkage code. It also doesn't use the in-kernel path for file caching that I mentioned earlier. The easiest way to do this is using a memory cache, but you can also do it using files directly that you access in user space, in which case the mechanism that you're using to access them isn't the same one that you would use if you were inside the kernel. So I mentioned earlier that you can do actual virtualization with KVM. So you do a complete build whenever you build on your test system, which in this instance will be your host. And the arbitrary guests that you spin up with KVM can run the same kernel and thus test the module that you just built. You can also do direct testing on virtual iron. So this works with basically any platform that you can virtualize. And the easiest platforms to virtualize are things that are x86 or x86-64 based, like Linux, BSDs, Solaris, and macOS. And what this means basically is that you have a machine that you will actually build a kernel module on and then install it onto the machine that is the worker. And because the machine is virtual, if it turns out you get yourself in trouble or trash the machine, you have the ability to roll back to a snapshot point. And what we've done is we've created known working configurations of the systems that we will be testing. And we start from this base configuration, build for it, install the actual kernel module into it, and then run our tests. And if it turns out something goes horribly wrong, either the test will wedge or crash. We've, in the process of testing, of course, encountered these. And either it will continually retry the test if the system crashes, or if it wedges, the test will simply not complete. And you can look at the console if you need to figure out what's going on, or use other native debugging tools for whatever platform you happen to be using. Obviously, you can use two kernel debugging on macOS. You can use the kernel core manager, core ADM on, or save core rather, on Solaris. You know, there are options for what you want to do if you have a system to debug that's in this state. But they're just the same as if you were actually testing it on a machine that was on your desk. So you don't actually have to do it because you have the test harness driving the actual tests themselves. So the way a typical run for us works is every night we have triggered nightly tests. And since the tests take long enough to run, that running the complete test suite for every patch set would preclude us from actually integrating large sets of changes into our tree. We basically, every night, in the middle of the night, we check out the current tip of our main branch. We generate autoconf artifacts. Our suite is basically uses autoconf to configure and drive our make files. Run configure, and then do a full build. At the end of that, as our last step, we run make check, and then we collect and analyze the results. In the simple case, obviously everything passes and there's not really anything to analyze. The answer is yes. So I mentioned earlier that the waterfall provides a 10,000 foot view, but it turns out you can drill in. And in this case, I've selected a builder. I selected a builder that is one of our test builders, and I opened it up, and you can see that 20 of the last 80 builds are available here. This is a new builder because Fedora 34 is a relatively newly supported system for us. And you can see that while the vast majority succeeded, that there are some failures, and there is a single exception showing here. And the exception is basically that the build was interrupted partway through before it was allowed to complete. In some cases, if something is taking too long, or if we've introduced a bug, we may choose to interrupt the system rather than letting it complete because we know that we've got a fix. Each one of these builds we have logs for, and as long as you've configured your system sufficiently, you can keep logs for as long as you like, and you basically have to pick and choose how much you're going to keep and when you want to expire them. You could actually choose to, in the event of success, just purge things after a week, but keep your failures around longer in case you needed to do further analysis. And we haven't really done specific optimization in this case, but we could do further optimization. If you drill down further, you can see that this is a particular build, and it tells you what version was checked out whenever we got the tip of the main branch, and that all of the steps passed at the high level view where they're just everything is green. And then it gives you the summary of what was actually done and how long it took. As far as results, if you actually click on any of the steps, it will show you the actual log of what happened. And we have our make step actually doing non-verbose output for everything that succeeds, and we only have verbose output for steps that generate warnings or errors. And then when we get to the point of testing, while at the end of the tests there is a simple summary, if you click on the actual test step itself, you get a complete log of all of the test steps. And this is just a relatively uninteresting snippet to show an example of a test running. And you can see that if you're actually able to see the fine text here, that we run the Solaris KLD test. And the Solaris KLD test is one of these tests that I mentioned earlier, where we're testing directly on the virtual hardware, where we copy in a kernel loadable module, we install the loadable module, then we mount the file system for which we needed to have loaded our module. We run a simple sample directory listing, and if the content is there, then in this case, we basically just shut things down, shut it off. In the time since these slides were written, we ended up enhancing this test because loading and unloading the module multiple times turned out to, in a certain case, display memory corruption from a change that we were working on. And an easy way of debugging whether or not we had gotten things right was to stop and start the client multiple times. And so this test now does that. So what we've learned: adding regression tests is very helpful, that it's really easy to end up in a situation where things that you fixed end up getting broken in another way in a complicated system like this. And this is good practice regardless, There were cases where it wasn't always easy for us in our previous test regimens to do it, and this has made it very easy for us to do so. Pay attention to your nightly builds. For the things that don't directly feed back into what you're doing as far as when you're submitting changes, it's very easy to end up in a situation where things get missed, and if you're not looking, your code suffers from bit rot. So make sure that, especially for the systems that you're not actually currently shipping to customers, that you actually are paying attention to what's actually happening. Retain your logs wherever possible. If you want to go back later and look and see what caused a failure that's an interesting failure, having that information available will make your life much better, and especially things where you're using Docker containers or KVM hosts where you're throwing away the virtual host at the end of the process. Making sure that you've saved the logs that you might want from those processes is an additional step that you might not have thought of and is important to get right. And snapshot known working configurations. Obviously, this is important for the situation where we're using these snapshots to start tests fresh from. But even in other cases, you want to make sure that you have things where you can go back and do analysis of what changed, where you want to make sure that what changed wasn't something where you took changes from upstream from whoever your operating system provider is or some dependency provider for your system. As far as future work goes, right now we use pre-generated Docker images, and we generate KVM images on the fly during the course of the build. And it would be nice to instead have triggered builds of Docker or KVM images that could then be used to optimize how we're testing things. In the case of KVM, not needing to build images on the fly and saving time. In the case of Docker, being able to easily update what's there in case there are reasons that we want to. And also, in the case of Docker right now, we don't actually have specific versions of our software in Docker. We always test the version that we have. So it would be nice to be able to have a repository of other versions so we could do arbitrary tests across multiple versions. Because for something like a network file system, ensuring that you're always maintaining compatibility over and above the ways that we already are is important. We don't currently have a hybrid of Docker and KVM or local to test kernel extensions, and that's another thing that would be nice to have in terms of being able to spin up infrastructure with Docker and then test a kernel extension against the specific servers that you just built in a multi-server configuration. And using pre-built binary images for Docker that another system generated in the same step in this process could allow you to avoid building for two different systems by cross-compiling. Because right now, for instance, if I want to run Docker images on a Mac, I would either have to cross-compile or pre-generate the binary images, whereas if I had the ability to trigger them, I could move things back and forth between the systems that I'm testing for. Lastly, I mentioned earlier that you could end up in a situation where one of the systems where you were testing on virtual iron, as it were, could end up in a crash and reboot loop. So having a watchdog system that used APIs available to you, whether those are VMware APIs or whatever cloud system you happen to be using to host your VMs, would be an ideal integration for this that we just haven't gotten to yet. So that's hands-off network testing, hands-off testing for network file systems. I'm Daria Phoebe Brashear, and I think at this point, I'd be happy to take any questions you have.